Okay, student, Assalamu alaikum. I decided to record another lecture for your online classes. And this lecture, as you can see on the screen, it's about fractional numbers or decimal numbers. Before starting today's lecture, let's talk about what we have covered so far. We have covered, the representation of signed and unsigned numbers in computer systems, their operations, their like operations like addition, subtraction, multiplication. We have also discussed about the casting, okay, how casting works in C language or in computer systems. So today is actually the last topic of chapter number 2, and it's about the floating point numbers. So let's see what we are going to cover in this lecture. The agenda item is about, first of all, we'll discuss about how fractional numbers or decimal numbers are actually represented in computer systems. And in this talk, in this particular segment, we'll focus on the IEEE format. We'll discuss what is the IEEE format for, to represent floating point number. Some background. Okay, let's use whiteboard. If you remember your early elementary, when you used to go to school and solve elementary mathematics problems, okay, most of time, like if you encounter, if like what, for example, if your teacher, class teacher, mathematics teacher, or write something on this on the board or screen, like what is that? It's a number, it's a numeric number, it's a digit, it's 2, right? I hope you are familiar with it, right? It is 2. But there are few things which are implicit or hidden in this digit. Nobody usually write it. Okay, what are those things? The first thing is here in this portion, and it is the sign of the number, the power, then two more things, one in the denominator, okay, and a dot over here, the point. Our today's topic or main focus is about talking about this dot. Okay, I just remember one thing. Sun Microsystems. Sun Microsystems was a big company, and their slogan was used to be, let me write over here, we are dot in com. Anyhow, so these are the four things which are generally we do not provide it, but we know about it. Like there's a sign. If it is a positive sign, then we don't write it normally. Okay. Then we have a 1 in the denominator. We have a power which is used to 1, and at the standard position there's a dot. Okay. So if I say it is a decimal number, so I can write it like this, 2.0. If I say it is a integer, then I just write 2. Okay, decimal numbers or fractional numbers can be of two types. What do I mean? I mean we can represent fractional numbers or decimal numbers, okay, with the help of fixed point or floating point. All right, so decimal numbers or fractional numbers can be represented in two ways in computer systems. One is a fixed point notation, and second is a floating point notation. And both have their pros and cons, obviously. Um, but in C language and C++ and most other languages, okay, we usually have floating point representation, and computer systems generally use floating point representation. So first of all, let's talk about fixed point representation. Uh, Fixed point representation means that the position of the point is fixed. Okay, like let me use, yeah, like for example, you have something like, for example, okay, let's discuss first of all the decimal notation, how we represent uh, a point or a decimal number okay, in decimal number systems. So you can see that this is the position of the point, okay, and towards the right side of the point, this is, a digit 1, digit 2, digit 3, and so on till minus n, and this is digit 0. Towards the left side of the point, digit 0, starting from digit 0, 1, 2, 3, and so on. Here, what we mean by uh, digit 0, digit 1, this actually represents the power of the base. Let's say that I have a number 24.31, for example, 24.31. Okay, so towards the right side of the base, towards the right side of the point, what we do actually, this is the number, okay, we multiply it with the 10 to the power minus 1. Then we have plus sign, 1 into 10 to the power minus 2. Then towards the left side of the point, we have 4, which will be multiplied by 10 to the power 0, and then we have 2, which will be multiplied by the 10 to the power 1. And if we add up all these things if we add all these terms, we'll get 24.31. How? 2 multiplied by 10 plus 4 multiplied by 1 plus 3 divided by 10 plus 1 divided by 100. We'll get 2 plus 4 plus 3 divided by 10 plus 1 divided by 100, and when we add up all these terms, we'll get 24.31. Sorry. Similarly, the same thing can be the same principle or same technique can be used in binary notation. Okay, in binary notation we have two things. One is the b represent a bit. B can be B is a set, okay, that may have 0 or 1, okay, first thing. And the base will be 2. The base is actually the term, the number, the digit multiplied, since it is binary, so it is 2. And here I is a power. So same thing, the same technique. If this is the position of the point, then any bit which is towards the right of the point will be multiplied by the 10 to the power minus n, okay, and towards the left hand side it will be multiplied by starting from 10 to 2 to the power, not 10, 2 to the power 0, and 1, 2, 3, and so on. Let's do some practice tasks. Let's do it over here. Let's suppose that I have included few practice tasks over here. We can solve it those things over here. So let's say that I have this number. This is a binary number 101.1111. It is not 11 actually, it is a binary number. And so if we expand it, okay, so it will be like, if I go back into the decimal form, so how can I go back? So this is the position of dot, let I have put it, but since it is, we are going into the decimal format, so the dot is not required actually. It will add up and it will convert it into fractional part. So this is 1 multiplied by 2 plus 1, sorry, plus 0, 0 multiplied by 2 plus 1 multiplied by 2. Then here says it was a dot, 1 multiplied by 2 plus 1 multiplied by 2. Now let's put the power. This was the position of the dot. Okay, so it will be -1, it will be -2, and here it will be 0, it will be 1, and it will be 2. So it will be converted into 2 to the power 1 into 4 plus 0 into 2 plus this power will be over here, 1 into 1 plus 1 upon 2 plus 1 upon 4. So it will be 4 plus 1, it will be 0, it will be 1 into 1, 1 times 1, it will be 1 plus half, and then plus 1 upon 4. So if you go and add up, you will get this number. Okay, any question? I hope if you have any question, you can find out the video, I mean time, you can refer to the time and you can ask me in the forum. Okay, the the one thing that you will notice, if we, I have purposely mentioned three set of same, same binary numbers, but the only difference over here that you'll observe is the position of the point. So if you pay attention, okay, if the point is actually going or moving towards the left hand side, okay, towards the left hand side, the the effect will be the multiply. You will be actually multiplying it by 2. Similarly, if the point is moving towards the right hand side, you are actually dividing it by 2. Okay. There is one more observation. Okay, if you have a number like numbers of the form 0, 1, 1, 1, 1, they are not equivalent to 1, but they are very close to 1. Okay, how? Let's do it. Let's solve it. For example, okay, let's take up to, let's say that I have a number 0.111111 and it is in base 2, and I want to convert this number into decimal or fractional part. Okay, decimal number system, I mean, when I say. So the technique of, converting this number into decimal number is same. You have to basically you have to multiply every bit which is actually towards the right of the point by 2 to the power minus times n, and every bit that is towards the left of the point by 2 to the power times m, starting from 0. So this is the only bit, so you will going to multiply it 0 multiplied by 2 to the power 0, then you have 1 multiplied by 2 to the power minus 1, then again 1 multiplied by 2 to the power minus 2, then again 1 multiplied by 2 to the power minus 3. So this is 0, 0 multiplied by 1, it will be 0 multiplied by 1 plus 1 upon 2 plus 1 upon 4 plus 1 upon 8. Okay, so this term will be discarded. Okay, so it will be 0 actually, and this will be converted into 8. This is 2. 2 means it will be 4. Then 4 means it will be 2 and it will be 1. That is 7 upon 8. 7 upon 8, when you convert it or divide 7 by 8, you will actually get a, a number which is very close to 1 but not actually 1. Let's say we do it. 7 divided by 8, you'll get 0.875, which is not 1, but this is very close to 1. Okay, now let's observe one more thing. Let's do it over here. For example, if I increase the number of bits after the decimal, okay, that is what we are talking about. If we increase the precision, you remember we had few things like precision, accuracy, something like that, right? So if we increase the precision, okay, what will be the effect? Let's say that I get, you know, I get up to two more digits, okay, after this, let 0.111, okay, and two more bits. So we know that this all these three bits will be all the left hand side, not the left hand side, the left term which is against the point will be 0, and up till now it will be uh, 1 upon 2, it will be 1 upon 4, it will be 1 upon 8. Then we have two more terms, 1 upon 16, I guess, and then I have 1 upon 32 also. If we add all these things, we're going to have 31 upon 32. Okay, and if I do the math again, 31 divided by 32, I'll get 0.9896, 0.96875. Okay, and previously it was when we had 7 upon 8, it was 8.875. So what we observe, actually, we observe that if we include a number of type of format or shape like this will be very close to 1, but it will not be 1. Okay, but the second thing that we observe is if we increase, if we continue to increase precision after the decimal point, we are getting close and close to 1. Like in this case we had only 3 bits, okay, after the decimal or floating point. So what we got 0.875, and when we increase the number of bits after the point, we got it more accuracy, we get more closer to 1. All right, so in this for how we can basically express 0.1111 all ones in binary, like, you know, like in this form, it is very close to 1 minus epsilon. You can consider it like delta or like any error or approximity. All right, okay, there are a few more, observations come limitation, that is about, when we represent numbers in, you know decimal, the fractional numbers or decimal numbers in computers. The one thing is, limitation number one is we can only exactly represent numbers of the form x upon 2 to the power k. Like what I mean that if, like, we can express a number, okay, that like I have a number, For example, any number, you can consider any binary number or any decimal number. But if we can basically express it in this particular form, then we can only represent it. All other rational numbers, if you remember rational numbers and irrational numbers, okay, all other rational numbers have a repeating bit representation. Like if I have 1 upon 3, if I have 1 upon 5, if I have 1 upon 10, what I get after few bits, okay, after few digits, okay, the number will go on repeating mode. Rational numbers and irrational numbers, rational and irrational numbers, there are two major categories of real numbers. Okay, so this is the one limitation. Like we can only in computer systems, we can only represent numbers that we can express in this form. If a number is a rational number and it is a repeating a rational number, okay, so we can actually just approximate those numbers. We cannot exactly represent those numbers. So here accuracy will get compromised, right? There is one more issue with the this particular model, like the fixed point model, in which the position of the point or period is fixed, is we can have only one arrangement, one possible setting. Like for example, if I have 8-bit vector, the size of the vector is 8-bit, and I say, okay, the position of my point will be at the fourth position, I mean halfway. Let's say this, I have half the bit towards the left of the point and half of the bit towards the right of the point. So here there, due to this fixed point representation, we can have different issues. One is the range issue. We cannot extend the range. Like we have 4 bits toward the left of the point and we have 4 bits toward the right of the point. So the maximum possible number, the integer part, can be 2 to the power 4. We have 4 bits, so it means it is 16 maximum. Right now we are in fact we are not considering about any bit for sign value. And similarly here we can go up to the accuracy of what should I say, yeah, not more than 16, 2 digit. So if we are using fixed point representation, so we do not have much uh, flexibility. Okay, so what happens in the early days, like 1980s and before that, every computer manufacturer used to have its own representation of floating point or point decimal numbers. So in 1985, IEEE, International Institute of Electrical and Electronics Engineers, they proposed a format or representation technique for floating point numbers. And they actually engaged few university professors. Actually, Intel initiated this project, and later on IEEE involved it, get into it, and we actually got IEEE standard for floating point number, which is 754. Okay, and now I'm going to start the second part of today's lecture, which is very important. So I think I should continue from here. Let me see, the time is 20 minutes, so okay. Uh, I know, I think some of you might remember it. When we talk about floating point numbers, we have the concept of exponent and mantissa base. Okay. So, okay, first of all, let's see a graphical representation of a floating point number. I'm talking about IEEE 754 floating point representation. First bit, or I can say that the first we'll see the sign bit, then few bits are reserved for exponent, and then few bits are reserved for fractional part. Here you you'll notice this thing, like exp is actually not exactly e, but it is a set of bits which are used to encode exponent. Similarly, the fractional part is not actually the mantissa, okay, or significant, but it is used to encode the mantissa or say significant. Okay, this is a generic format. Okay, we have -1 to the and having power sign. If sign bit is 0, it will be positive, and if sign bit is 1, the number will be negative, floating point number. Then we have a mantissa and then 2 to the power e exponent. Okay. Okay, so this is another picture taken from the book, and this is actually the representation for 32-bit floating point number, which we used to have, like if when we use C language and we declare a variable with the help of float. Okay, like float f semicolon, and if we declare another variable with the help of keyword double d semicolon. So this is a 64-bit representation. Double takes 8 bytes and float takes 4 bytes. So in 4 bytes, if a floating point number takes 4 bytes, so the first, I mean the MSB, we can say that is reserved for sign. Then we have 8 bits for E or X, not actually exponent, but we can say that exponential part, and the remaining, I guess, 23 bits for just 23 bits for fractional part or mantissa. In double precisions, 1 bit is reserved for sign. Then I guess I have written somewhere, um, yeah, k, which is exp. The size of exp is 11 bits. Here we have 11 bits, and then we have 52 bits for fractional part. All right. K is a generic term. Actually, K is just a variable, but we generally use will use in our example that when we say K, it means that it is E or exponential part. We are referring to E or exponential part. All right. So depending upon, I mean, what is present in. Okay, let's first of all let's consider a 4-byte uh, variable. I mean, 4-byte floating point number, let's say float. And in those 4-byte or floating point number, the size of exponential part or e, small e, I mean, is 8 bits. The size of exponential part k is 8 bits. So based on what is encoded in those 8 bits, we can have 3 different variations. One is a normalized form, one is denormalized form, and one is special case. Third one is a special case, which in turn have 2 different subtypes. And we'll shortly see that how these 3 variations or 3 different, uh, we can say that the encoding, floating point encoding uh, are used to represent the whole bunch of floating point numbers. So let's talk about case 1, normalized value. Remember, the basic formula is here. V, which is a vector used to represent a floating point vector, minus is equal to -1 whole power s, represent s sign. M is mantissa or significant, and then we have a 2 to the power e is exponent. So in the normalized value or normalized case, the k bits or exponential part should not be equal to all zeros or all ones. right? Here we cannot have exponential part all zeros or all ones. Okay, this is the first, this is a law, or this is the rule, you can say that. So it means that if we have an 8-bit number, okay, and we exclude 0 and 255, so the possible maximum range will be 1 to 254, right? For single precision or 4-byte number, sorry, 4-byte floating point number. But if we have, a double precision floating point number where k becomes 11, so in that scenario, the size will change. The possible unique code vector can be maximum 2046. Here it can be maximum 254. Now, one thing that we'll discuss in the in a Q session in more detail about bias. Bias is, you can think about, it actually, it is, remember, sign representation, uh, sign numbers, like, sign numbers are generally used, uh, two's complement encoding, if you remember, and we have studied it in much detail. You know that when we talk about a number of this particular form, like, let me write it over here, like if I say that 2.37 multiplied by 10 to the power, let's say that x. If I'm saying that I want to encode my floating point number in this, by converting it into this form, so here I have to manage with two signs. One is the sign of the mantissa, okay, and the second is the sign of this power. So the sign of the mantissa, or sign of the, the magnitude, is actually, managed with the help of the sign bit. But how we can actually, these 8 bits are used to encode the exponent. So how we can actually manage the sign of the exponent? One simple approach that you may come up with, and you say that, okay, we can use two's complement technique. But later we'll see that why two's complement technique is not a very efficient technique when representing a sign exponent for floating point numbers. So we not I mean, when I say we, I mean the scientists actually, or the system architects at that time, you know use the concept of bias. Okay, bias is actually a number that can basically shift your from one domain to another domain. Like, you might have you have studied digital signal processing and electronics as well. So let's say that you are receiving a signal like this square wave. So the signal is actually, and let's say that the zero is here, the line drawing I'm drawing it, and this is -1. Let's say this is +1 and this is 0. So you can say that, you can think of bias is like that. It is converting or shifting you from one quadrant or one side, from one side to another side. So the calculation of bias is very simple. The formula for the bias is this: 2 to the power k minus 1 minus 1. So here k is 8. Okay, 8 means to the power 8 minus 1 will be like 8 minus 1, 7 to the power 7, means 128 minus 1. I'll get the value of bias is 127. This is the value of the bias for 8-bit if we have E8. And if we have 11 bits, the size of k is 11. So we can have bias value 1023 maximum. So this is the way how we, okay, now the formula to encode exponent. This is the formula. What we do actually, whatever we got the value of exp, I have to subtract it from the bias. For 8-bit, I have a bias 127. So eventually I'll get the exponent. I will see shortly in an example how the bias will be calculated. Now, the second thing is how to encode the mantissa, or how to encode significant. As you pay attention, I hope you have paid attention to my earlier words. This fractional part is not storing mantissa. It is used to encode or used to represent mantissa. Like, it actually, f is not actually equal to m, but f is actually trying to store m within it. Okay, and similarly that's true for exp as well. These 8 bits of exp are not storing exponent. It is not storing actual exponent, but they are trying to encode uh, or represent exponent. Like, okay, I'll give you an example. I say that I have a number, a floating point number, that had an exponent, for example, +4. So if I have exponent 4, it means that the if I want to encode this 4 into an 8-bit number, so it will be 0 0 0 0, one more 0, and 1 0 0. Okay, so this is 4 in decimal and this is 4 in binary. 1 2 4, 8 16, and so on. But in reality, when you dissect a floating point number which had an exponent 4, you will not see this bit pattern over here. You will see a different bit pattern. That's why we are saying that exp, or short for exponent e, and fractional part are actually going to represent exponent and the fraction mantissa, but they are not actually storing it in literal sense. All right. Okay, so let's talk about how mantissa is encoded. For normalized values, for normalized case, we assume that we have to convert, or you have to convert the what I say, the actual magnitude of mantissa in this particular format, like one dot, I mean 1 point. This is in binary. Okay, remember 1.1010, something like that, and in the binary. Okay, let me explain with an example. So we have given a number, float f is equal to 15213.0. I converted this number into binary. Okay, so let me count how many bits are there. 1 2 3 4 5 6 7 8 9 10 11 12 13 and 14. So total we have 14 bits. Okay, remember, if all these bits are, if this is binary and there is no point, so I'll assume that the point is over here at the end. Okay, like if I have written 2, as in the first slide you saw, that means that my point is over here. Okay, now my what mantissa says, or I can say that what my fractional part says, that I have to convert this binary pattern into this particular format. Sorry, it can be 0 1 format. I mean, it can be 0 1 0 1, like I can say 1 x x x x, something like that. till x2. Okay, so if my decimal point, not decimal, my binary point is over here, right, at the last position, and I have, total number of bits 14. So if I convert it into this particular format, how can I do that? I have to shift my binary point from right to left. Okay, so when I start shifting my binary point from right to left side, so remember the rule, I have to multiply by +1 every time. Okay, so and I end up over here in 1.1101 format, which is required. So I incremented every time the power of 2. So there were 14 binary bits, so I just added over here, so I have to increment the power of 2 till 13. So this will become mantissa. Okay, now one more thing that you need to pay attention, this 1.111101101101 is actually my mantissa, significant. But when I encode it into fractional part, remember the 23 bits of the fractional part for 4 byte floating point number, I will omit this one, because I know that in normalized encoding, every time my fractional part will end up in this, my mantissa will end up in this format. So let me go back to this slide, previous one. So this is over here, this one, because we know that there must be a 1, because we hard coded it into our computer architecture. So I can omit it. The benefit is we get one free bit. Okay, so minimum when fractional part will be 0, m can be, what is the minimum value of the fractional part of the mantissa? It can be 1.0, and it cannot be equal to 2. Okay, but very close to 2. Okay, now time to calculate actual exponent and the bias. For 8-bit number, we know that the value of the bias is 127, and here the exponent is 23. Okay, now we have, when we actually convert, okay, 120 by using this formula. Okay, so we can calculate the exponential part, and it will be added 1 e plus bias, it will be 13 plus 127, end up with 140. You got the idea? This example is used to show you that how you will going to basically represent a 4-byte floating point number in computer system. So we can apply a reverse gear. Okay, let's suppose that you got this number, this bit pattern, 4-byte long, 32 bits, and I tell you that this bit vector is actually encoded with IEEE 854 encoding technique, right? You got this bit vector from me, and I say this vector is encoded with IEEE 854 encoding technique. So you can actually convert this bit representation into actual decimal number. All right, so let's do it. S is 0, means it is a positive number. Okay, we got 8 bits for exponent, right? So if you know, this is 4, this is 8, end up with 12, and this is 128. Okay, so you will get 128 plus 8 plus 4, you will get 40. Exponent will be 40, and then you got, this for mantissa, this whole 23 bits. Okay, so when you will convert all these, bits, you will actually get this 15213. uh, I I think I should leave the reverse process of converting a bit vector uh, encoded in 854 floating point representation into decimal for you as a homework or a practice task. Let me see the size of the recording, how much I have. Okay, I think I should finish it in next 10 minutes, and let's go talk about denormalized values, and the last is, yeah. Okay, so second case of floating point format IEEE 854 was denormalized form. Denormalized form is a form when you get all the exponential bits 0, and this form is actually used for two particular purposes. One, it is a way to provide you, or it is a way to represent 0, actual 0, 0. When I say 0, I mean 0, 0.0. Okay, and the second function of the denormalized form, denormalized representation, is to represent numbers that are very close to 0 but not actually 0. Okay, so let's see what is the difference. Here, first of all, you need to remember that all the 8 bits, okay, of EXP will be 0. Okay, and sign bit can be positive or negative. That is not the part of EXP. Here we have some different formula to calculate exponent. We just subtract, uh, in order to calculate exponent, we get this formula 1 minus bias, and for 8 bit, if we have k is equal to 8, so we'll get 127 as bias. So every time uh, we have actually, well, what is it, 1 minus 127, I get e is equal to minus 126, which is the exponent. Okay, now the cases. Okay, the cases are two. When we have, okay, you know that exp or exponential part will be 0, so the only thing which is left is fractional part. It can be 0 or it cannot be 0. I mean, 0 means all the bits should be 0, and if it is not equal to 0, it means that any of the 23 bit is not 0. So if we get all the bits 0, so it actually represents 0 value. Okay, so, and if we do not have, if any bit is not 0, so we actually do not have decimal 0, but a number which is very close to 0. Okay, we'll see in detail We can have few questions over here about, we can discuss about positive zero and negative zero. We do not have any distinction, okay, in positive. In fact, the floating point representation of plus has a bit pattern of all zeros. The sign bit is zero, and the exponent field is all zero, indicating a denormalized value, and the fraction field is all zero. Okay. Curiously, when the sign bit is 1 but the other field are all 0, we can have a negative 0. Okay, so you know with, with due to this sign bit, okay, we can have a positive 0 0.0, and if this bit is set, we can have a negative 0.0, but eventually 0 is 0. Okay, well, I have added one more point over here. With IEEE floating point format, the values minus 0.0 and the plus 0.0 are considered different in some ways and same in others. Okay, since the with the normalized numbers, we must always have m is greater than 1, and hence we cannot represent 0. Just true. Okay. If you have any query regarding these points, we can discuss during the class Q&A session. Similarly, like the in denormalized form, as I mentioned earlier, the one reason is to use denormalized form is to encode 0, and the second is if the fractional part is not all zeros, but we can have a number which is very close to 0. They provide a property known as gradual underflow, in which possible numeric values are spaced evenly near 0. Like I think I have added a number line at the end, so we can have some discussion about it, like equi-space. We can have some discussion in QA. All right. So the case, uh, last case for floating point number IEEE 854 is when you have all the bits are set in exp field. Okay, like in the previous case, denormalize, we have all the bits zeros, and here in the in the third case we have all the bits set. So here, as you can see, that if we have all the bit sets in the exp field, so again we have two options, whether the fractional bits are also 0, if all zeros, and if they are not equal to 0. Okay, any of the bit. So if all are 0, so it represents infinity, and okay, we can see if all bits are set in the not set in the fractional part, so this is the case A, it represents infinity. Okay, and whether it is a positive infinity or a negative infinity, it is actually decided by the sign bit, the MSB. Infinity can represent results that overflows. Yes, obviously, when we multiply two very large numbers, or even at times if we are going to add two very large numbers, something like that. And one more way of mathematical rule, like if you divide any number by 0, 2 divided by 0. Okay, so these are the few examples. 1.0 divided by 0.0, we get a positive infinity. Minus 1.0 divided by minus 0.0, we got positive infinity. And again 1.0 divided by minus 0.0, negative infinity. The second case is the last case actually, and last special case. We have two special cases, and in this case if any of the bit in the fractional part is not set. Okay, previously, if all the bits are zero, or we can say not set in fractional part, it will going to represent infinity, positive or negative. But here in the second scenario, if any of the bit in the fractional part is not set, means 1, then it means it is not infinity, but it is some special case and it represents not a number. Then, okay, like for instance, we have imaginary, we usually come across imaginary numbers, sqrt, you know, -2. We are going to add to infinity, so it is not a number at the end of the day. If you are going to multiply to infinity by 0. Okay, so this is a one use case where we can use special values, like for example, if we do not want to initialize uninitialized data, so not a number is a good option. Like you want to ensure that if you are using a floating point number and you want to ensure that that number must not be that is uninitialized unless I don't you have not initialized it, or you are not going to initialize some part later in the code, so you can explicitly uh, hard code it as not a number. Okay, visual representation is very simple. This is a number line. You're familiar with this. uh, you know Here we have actually denormalized. First of all, if we want to represent a zero, either positive or zero, we must have to use denormalized form. Okay. Secondly, if we want to represent a number which is not zero but very close to zero, either from the negative side or either from the positive side, so again we're going to use denormalized form, right? Anything beyond that, like from the negative side or from the positive side, numbers which are not close to zero and not infinity, so those floating point numbers will be represented by a normalized form. And lastly, if we have infinity or something beyond infinity, not a number, we are going to encode those numbers with case 3, right? It doesn't have a special name, but or like normalize, denormalize. You can you can say, okay, it's unnormalized. Anyhow, questions are welcome. You can post it on the forum and I upload the video, I mean the screencasting, or I think we can have a QA session on this lecture, which I'm recording at the moment, on Monday. I guess I think Monday will be a good option. Like there are two things. When the first thing is where I can give you I can relay this lecture in the lecture timing. That is also a possibility, or I can upload it before the lecture. I think that will be good. And during the lecture we can have a QA on. Thank you. I hope you enjoy it.